Okay, gang, welcome back. Today is class number 28. Project number 3 is due right now, so throw it in the folder. Even if it's incomplete, throw it in the folder. Whatever you've got right now, throw it in the folder. Today and on Wednesday, we're going to talk about rational functions and their graphs. Rational functions are going to be the most complex functions that we have graphed together. So as the semester progresses, we ratchet up the complexity, which seems reasonable. Coming up, just a sneak peek after these 2 days on rational functions, 2 days on exponential functions, whatever they are, and 2 days on logarithmic functions, whatever they are. And then before you know it, will be test number 3 just after Thanksgiving break. I will give you a take-home quiz at the end of this week on Friday that you'll turn in on Monday. Any questions on the calendar?
What do we get for Thanksgiving break?
Thanksgiving is Thursday, Friday. We will have class on Wednesday, November 23rd. Yeah. Other questions? Okay. All right, so let's get started on page 40. And we're going to jump here to the middle on the demo. It says a rational function. So we're defining this brand new function for us. A rational function is a ratio of two polynomial functions. Here's an example right here. It is a ratio of two polynomial functions. Ratio just means division. So I've got a polynomial on top and a polynomial on the bottom. It happens in this case, the two polynomials are in different forms, right? Factored form on the bottom, and I think we call it standard form on the top. But anyway, ratio of two polynomials. That is a rational function. It's a little bit unfortunate. The word rational in a non-math class just means logical or you know, like making something make sense. It's rational, right? That has nothing to do with this. What word do you see in the beginning of rational? Ratio. That's why it's called a rational function, not because it's more logical than anything else. It's just a ratio, okay? Ratio. Aaron, you had your hand up.
Yeah, this was on the.
Uh-oh, is that true? Anybody else?
It was like talking about like parts.
Rule of signs?
Yeah.
Hang on. So there was a note. Hold on, there's a note on the previous activity. Maybe we didn't all see it. On page 36, so this is a few pages ago, says the directions for the class 29 homework, that's the one that was due today, say to use the rational zero theorem, Descartes' rule of signs, and possibly the graph of the polynomial function shown by a graphing utility as an aid in obtaining the first zero. It says you can ignore the parts about the rational theorem, the rational zero theorem, and Descartes' rule of signs. As we did in class, you should use a graphing utility to graph the polynomial and find a nice rational zero of the polynomial. And then once you have 1 0 in your hands, then you do the process just like we did in class to do the rest. Does that help? Does that?
We also talked about like sign changes and stuff like that. Which I didn't know that.
Yeah, we didn't talk about sign changes here. I don't know what the homework looks like. I'm going to be honest here. So help me out. Other folks have the same opinion? And so, yeah, no, an hour is good. I want it to take an hour. Okay, so let me. I'm not sure what to do about that assignment. I'll go take a look at it. When it had references to the rational zero theorem and Descartes' rule of signs, like were there like specific parts that you had to answer using that, or did the updated directions here make sense?
Like, part of the problem is a lot of math that I don't understand the class. It's like,
Yeah.
I do think that's a lot. The problem with this one is that
Stuff that we didn't cover. Right.
so, like, I figured it out. Positive.
Yeah. Okay. So like I hear what you're saying about how the show me how to solve this isn't going to help you when it's solving it in a way we're not talking about. Yeah, I get that. Other feedback from me? I'm going to look at the assignment after class, but if it needs adjusting, then I can adjust it.
I did feel like it went to a step further than what we went last.
Okay.
There was some material. Yeah. Give you like 3 different things. After you have to solve that, and say like equals x equals -1 equals 118. And see get that correctly.
Okay.
Definitely.
Look different. Yeah, okay. All right, I'll take a look at it. All right, I will get back to you next class after I've had a chance to look at that homework. Okay, let's come back here then to page 40. Okay, and so for better or worse, the stuff we're doing today has nothing to do with the stuff that we did last time. So no division, no synthetic stuff. It's really completely separate. So hopefully any confusion we had in the past classes or homework won't carry over today. Okay, so number 2 talks about domain. We know domain is the set of allowable inputs, typically the x values. There's really only one issue with domain in terms of a function like this. Typically domain is associated with like, you can't take the square root of what kind of a number? Negative. You can, but then you're in imaginary land, right? Which is okay, but it's not where we typically are. And you can't divide by 0, and every rational function has division in it, and so there's always this potential of dividing by 0, which is a problem. And so when we say what's the domain of a rational function, we're really saying, hey, what values of x make the bottom 0? And whatever you get, you're going to toss them out of the domain. So that's all. So I'm just going to copy the bottom as it is. And I'm going to set it equal to the magic number, which is 0. And then we're going to solve. We'll start on the right. What value of x makes the last parentheses equal to 0? -2. Someone else, what value of x in the middle? 4, right? Sometimes folks don't know what to do with an x sitting by itself. 0. That's what makes it 0. So are these 3 x values in the domain or out of the domain? They are out of the domain, because any of them plugged in gives you a division by 0. So that means the domain is equal to, will be, so I'm just going to say x not equal to 0 and 4 and -2. But if we want to be really fancy and use that set builder notation, that's a more complete answer there. So in this rational function, we set the denominator equal to 0. What did we completely ignore in that function? Is the numerator. And it feels weird in a math class to like completely ignore one part in favor of the other part. That's what we do. Could care less about what the numerator is doing. It's just about dividing by 0. So it's just about the bottom. Okay, number 3. Let's investigate what happens near a value that is excluded from the function's domain. So in the previous case, x equals 0 or 4 or -2. I can't plug 4 into that original function, right? But could I plug in 4.001? Sure. And so the question is, what happens to that function if I plug in 4.001? Because something strange happens right at 4, right? Like it's got to do something legal at 4.001, but then all of a sudden, poof, it vanishes, it ceases to exist at 4. So what's happening in that sort of transition period? That's what we're after here. So what we're going to do is start with a simpler rational function than that one. We're going to start with 1 over x. We currently have like a toolkit of basic functions that we just know what they look like cold. For example, y equals x squared. Right, we played the game the other day where we stood up and do this. So we know x squared, we know x cubed, we know y equals x, we know y equals the square root of x, right? We've been playing around with that function and we know how to shift it and stretch it and all that stuff. So we are about to add to our list of basic functions that we just know cold. We're gonna add 2 new ones. This is one of them. So y f of x equals 1 over x. So first of all, let's find out what value of x is excluded from the domain. 0, because that's the division by 0 we're trying to avoid. Okay, let's go to the next page. So if we asked for the domain, that it would say everything except for x equals 0, but that question I think said what's excluded. X equals 0 is excluded. So let's fill in the table of values to see what happens to the y values of this function as the x values get closer to the excluded 0. X equals 0 we cannot do, but we could do x equals 1 or x equals 0.5 or x equals 0.1, 0.01 or even 0.001. As long as it's not 0, we can plug it in and get a number. Okay, so we can do most of these without a calculator, possibly all of them without a calculator, and it might be more meaningful what we're going to do here if we think about it and don't use the calculator. If we plug in f, what do we get for f of 1? That's 1. F of 0.5, don't shout it out. Let's give folks a chance to think about it. We're doing 1 over 0.5. Might be easier to think of that as 1 over half. 1 over half. 1 over just flips whatever is on the bottom. Right? Whatever's on the bottom, we can flip and bring it upstairs. So what is 1 over half? 2, right? 2 over 1, which is just 2. Okay, again, this next one, don't just shout it out, but this is really saying 1 over 0.1. My flipping thing is helpful if I can get the denominator as a fraction. 0.1 is a tenth, yes? So flip, and what do we get? 10. So the y value there, the output is 10. For the next one, I've got 1 over 100th, which I'm going to choose to write as a fraction, not a decimal. What is it? This is 100. 1 over 1,000th is 1,000. What is happening in the top row? The numbers are getting close to, top row first. Numbers are getting close to 0. That was the idea. What's happening to the numbers in the bottom row? Very, very big towards what idea? Infinity. That's the idea here. So as the x values approach 0 from the right, the values of f of x approach infinity. You don't need to put a positive sign in the front, but I will just to highlight that we were getting positive 100, positive 1,000. And then there's shorthand notation for that sentence. It's as x approaches 0, and then there's this little funny plus sign. Now that looks very strange because typically plus signs and minus signs go where? In the front of a number. That's not what this means. This is to the right of the number, and it's small, and it's like a power almost. But what that means is that we're plugging in for numbers for x that are close to 0, but all of them are close to 0 from the right of 0. So if you're imagining a number line, there's 0, and here are the numbers that we plugged in. We plugged in 1, and then we plugged in 0.5, and then we plugged in 0.1, and all of these numbers are to the right of 0, yes? And so that's what we mean when we have a little plus sign up there. It's 0 from the right-hand side of 0. Okay, in the table below, let's see what we get here. Same f of x function, but now we're going to plug -1. What do we get? -1 there. And then -0.5 gives -2. And we can probably see the pattern by this point. How do these numbers relate to the previous ones? They're just the negatives, right? So -10, -100, and -1,000. In the top row, x is approaching what number? The top row first. X is approaching 0 from which side? From the left side of 0. And what's happening to the numbers in the bottom row? Approaching -infinity. And so that's the blank here. As x approaches 0 from the left, the values of f of x approach -infinity. So positive infinity from the right, -infinity from the left. And then just like before, we had our shorthand notation. As x approaches 0 from the left, it's not -0, it's saying 0 from the left. F of x approaches -infinity. And so when we graph this thing, we're going to see in a second vertical asymptote. So we'll talk about that when we graph it. So let's come down here in number 4. It says we know what happens near x equals 0. Either we go towards infinity or towards minus infinity, depending on the direction. So here are some other characteristics of the graph. Does f of x have equals 1 over x have any x-intercepts or y-intercepts? We'll do them separately. To find x-intercepts, let's actually do y first. To find y-intercepts, we let what equal what? X equals 0. So to find the y-intercept, we're letting x equal 0. So that means we're just doing f of 0, right? What is that? 0? It's 1 over 0. Yeah, that's no good, right? We can't, I mean, we knew we couldn't plug 0 in. That's something we established early on. Okay, so, oh, that's a scary, sad face there, my goodness. It's all warped on the one side, you know. Okay, so this guy right here does not exist, which means there are no y-intercepts. To find x-intercepts, we let what equal what? Let f of x equals 0 or y equals 0. So to this piece here, I'm going to do 0 equals the original function. Okay? And so I want to know what value of x can I plug in to solve that equation. Jed says no, he's just shaking his head. Can't do it. Can't do it. There's no way to plug an x in there and get 0 as the answer. If you wanted to do algebra, you could get this x out of the denominator by multiplying both sides by x, right? And what do you get when you multiply both sides by x? 0 equals 1. That's a problem. That's a hint that there's something fishy there. But even without doing the algebra and getting to 0 equals 1, you can look at that and say, okay, the only way a fraction is equal to 0 is if which piece is equal to 0? It's the top. For example, 0 over 7, or 0 over 73, or 0 over negative 731, right? All of those are equal to 0. But that's the only way to make the fraction equal to 0. As soon as you put a number on the top, like 1, we're done. It's not ever going to equal 0. So that means there are no what? X-intercepts or y-intercepts. Got them both now. Okay, let's talk about end behavior here for f of x equals 1 over x. So end behavior means at the far left and the far right. So we're going to pick really big numbers for x and plug them in and see what the y's are doing. And we're going to pick really small numbers like close to negative infinity, plug them in and see what the y's are doing. So let's try it. F of, okay, let's pick a big number to plug in for x. 1,000. So this is thinking about what's happening at the far right of this graph. So plugging in, we get 1 over 1,000, 0.001. Let's pick a bigger number. F of 100,000, which is really 1 over 100,000, which is 0.1234. Do I have that right? I think that's right. So what are the y values doing as the x gets bigger and bigger? Closer to 0. Will it equal 0? No, we've already seen that we can't make the fraction equal 0. That's in orange up there, right? We can't do that, but it's going to get closer and closer to 0, as close as you could possibly want. Okay, just while this is up here, I'm going to cheat and do the left side at the same time. If I plug in negative 100,000, thinking about going to the far left, I get 1 over negative 100,000, which is negative 0.00001. So when x goes to the far left, what's happening to the y's? Closer to what number? Are they?
0.
Closer to 0. So whether you go to the far left or far right, the y values are approaching 0, either way. And so I think it said use arrow notation. So as x goes to infinity, f of x goes to what? 0. And as x goes to minus infinity, f of x goes to 0. Okay, let's put all of these pieces together and create a brand new function, which again is now going to get added to our list of, oh, I know x squared, I know x cubed, we're going to know 1 over x. Okay, what we saw was that as x approached infinity, the y's were approaching 0. And what kind of numbers were we getting here, positive or negative? When x was positive, we're getting positive, right? Close to 0, but positive. So what that means is that these numbers here are coming in like this. As you go to the right, the y values are getting closer and closer to 0. And they're all positive y values, which is why I've drawn this thing above the x-axis. Let's go the other side. We'll leave the sort of gap in the middle here. As x goes to minus infinity, so in green, we're still going to 0. But what kind of numbers when we plugged in like negative 100,000? It was a negative number. It's close to 0, but it was negative, yeah? So as I go to the left, I need to get close to 0, but from the negative side, from underneath. So like that. Okay, and then the rest of this is just sort of the in-between behavior. What we saw in the very first table on this page, as x approached 0 from the right, what was happening to the y's? They were getting bigger and bigger and bigger, and so here's how we draw that. As x approaches 0 from the right, I'll draw it in pieces here. As x approaches 0 from the right, the y values have to go up to infinity. And so we just put those two pieces together and continue this curve up that way. And on the other side, same idea, but down to minus infinity. What do you notice about intercepts? None, which is what we saw before. No x-intercepts, no y-intercepts. It never hits either of the axes. The x-axis is called a horizontal asymptote because at the far right, the graph gets really close to that x-axis, right? Also happens at the far left, it gets close to the same x-axis, so that's a horizontal asymptote. What's the vertical asymptote in this picture? Is the y-axis, because the graph gets really close to the y-axis, but never hits it. And I'll point out one thing. Somebody, maybe it was Jamie, mentioned about the troublesome homework assignment about the sign changes. Maybe it was Aaron. Talked about, did it mention sign, like stuff about signs? Yeah, so let's talk about signs here. Imagine you were going to just draw this graph from left to right. So, okay, easy enough. I start out here. I'm just drawing left to right, left to right, left to right. Technically, there's no last point here, so in theory, I never finish drawing. But at some point, I'm just going to get tired of drawing here. And then what happens when I go to the right, just a hair, to get to the next part of the graph? Where do I go? I go from infinitely far in the basement to infinitely far up in the sky, right? And so it's just like this really smooth, nice, no problem, no problem, no problem. Oh my gosh, whiplash as I go from the one side to the other side. And so that right there, that whiplash moment, that was a sign change. We went from something negative to something positive, and it happened, you know, in sort of in the blink of an eye. Right? And so there was definitely a sign change as we went from one side of the y-axis to the other side of the x-axis, of the y-axis. And we'll talk more about that in next class, but the sign changes are supposed to help us graph. Okay, I think that that is good. What kind of symmetry does this graph have? It's going through the origin, right? It's symmetric over the origin. What word did we use for that? Even or odd? Yeah, that was odd. Odd was symmetric through the origin. So this guy right here is odd. Odd. And it's symmetric through the origin. We're not going to verify, but it's a fact about that graph. Okay, on the next page, I promised you 2 new functions to add to our toolkit. Here's the second one for today. is f of x equals 1 over x squared. The only difference here is that it's squared in the bottom. And we're not going to run through the entire argument again. Everything is almost exactly the same. Let's say another way. Almost everything is exactly the same. There is only one small change. If I plug in, for example, 3, what do I get? 1/9. If I plug in -3, what do I get? We also get 1/9. And there's no way we're ever going to get something negative as an output because that squared makes everything positive, right? And so which of the two pieces, we had this branch in the first quadrant and another branch in the third quadrant, which one just can't possibly be right for this graph? Is the third quadrant, because we can't ever be below. We can't have any negative y's. But all that happens, and we do get y's over here, but they're all positive, right? And so just imagine taking the branch that's in the third quadrant and flipping it where? We'll just flip it right up to the second quadrant. That's what we're supposed to have. So it's going to be exactly the same graph. We're just going to skip to the punchline right here. Exactly the same, I say exactly the same, is going to look very similar in the first quadrant. But in the piece that used to be, I'll put it down here, this is what it used to be. But where is it now? It's up in the symmetric second quadrant. So there's the rest of that graph, okay? So the orange piece is not part of this graph, just sort of reminding us of what we had for the previous function. And the relationship between the graph here and the graph of 1 over x that we just did on the previous page reminds me of the standing up day. We said that y equals x was this, right? Opposite ends. I'm doing this right? Yes, this is from your perspective. Everything's backwards for me. Okay, so there's y equals x squared is here, right? Y equals x cubed is that, x to the 4th, x to the 5th. So it's the same kind of idea for me, except instead of looking like this, the pieces just end up looking like this. But 1 over x is here. 1 over x squared is there, that one, right? 1 over x cubed is looking an awful lot like 1 over x. And 1 over x to the 4th is back up here. So it's sort of the same idea, right? If it's an odd thing, we had opposite behavior, even same behavior. It's still true. Odd thing, opposite behavior, even same behavior. Okay, one last thing, and then you'll do the activities. Suppose that I give you this function right here, x minus 5 over x minus 5 times x squared. Can we reduce? What do we get when we reduce? 1 over x squared. Really common for folks to say x squared. It's not x squared. X squared is in the bottom. We need to put a 1 over. So if I asked you to graph this original guy, what would you draw? That, right? Because it's just the same as 1 over x squared, and we know 1 over x squared looks like that. There is one subtle but important difference between the graph of this thing here and the graph of this thing here. One difference only. What's the domain for this first guy? All the x's except for what number? 0. What about over here? 0 is still no good. What about 5? 5 is no good. If you try plugging 5 in, what do you get? 0 on the bottom, which is a problem. Even though we all know we can cross that thing off, it still came from something where 5 was a problem, okay? And so if I'm looking at my graph over here, at x equals 5, I don't know what's going on, but it can't just be plain old, you know, the picture that we've drawn there, because at x equals 5, we're just not allowed to plug the thing in. Jed? Well, let's look. So let's plug in 5. So on the bottom, it was 0 times 5 squared, right? And on the top, when we plug in 5? 0. So what would you say if you met that creature? What is that equal to? Yeah, this is like two opposing answers. We know 0 over anything is how much? Like 0 over 7 is 0. But we also know dividing by 0 makes the thing undefined. And there's a conflict here. Which one wins? It's undefined. Like I cannot give meaning to that thing. Even though you have a rule that says 0 over anything is 0, that rule is not valid when the bottom is also 0. And so for sure, we're not supposed to like cancel these guys off. Like you can't cross them off. So the thing is just not defined. Undefined. Which means at x equals 5, I cannot draw a point. I can't put a point anywhere on that graph at x equals 5. So I got to take my eraser and go to x equals 5 and blank it out. Now I have blanked out way too much. I should only be blanking out the one point at x equals 5. X equals 5.1, no problems. 4.9, no problems. But x equals 5 does not exist. It is undefined. And so how do we symbolize that a point is not quite there, but we know exactly where it's supposed to be? It's just an empty circle. Okay. You have to do it. You have to draw it everywhere else. I mean, just cancel the thing out. X minus 5 does not belong there, and it just looks like it makes the thing more complicated, but it doesn't. You get rid of it. But then you have to represent it, and you say, hey, I'm not allowed to plug in x equals 5. There's a hole right there. And it's also your job to recognize where that hole is. How could I know the y coordinate? Because I just said we're not allowed to plug in 0. How would you find the y coordinate over there? So we can't plug 5 into the original, but we can plug 5 into the reduced version. What do you get when you plug 5 into the reduced thing? 1 over 25. That's where the hole is. Because we know what the graph is doing everywhere else except x equals 5, and we know it's doing 1 over x squared. We know it behaves like 1 over x squared. So 1 over 25 is right. You got to make sure you know how to find that y coordinate, because that's where you plot your point. That's where you plot the hole. Okay? Any questions on that? Okay, activity starts on the next page. Let's see how far we can get. If you finish everything, then you're going back to some previous section which was problematic.